hit record so that that's going, and share my screen, and we'll get moving. Share. Excellent. Make a file. Okay, here we go. So we have some number on our usual worksheet. And then I also made a huge list of my own of problems that I think are sufficiently nasty and evil that they'll make good practice. So the first one has to do with, as you could tell, sugars. And here it is. Well, what do you guys think? Oh, oops, not what I wanted to do. Uh-oh. That was not my point. Okay, I wanted to make this smaller, but I didn't know what I was doing. All right. Okay, well, the document is slightly tilted now because I messed up. Let me copy it back in. Sorry. Okay. Now here it is. Okay. So what's going on?
So this will just be like esterification of that alcohol, the acetyl carbon alcohol. Yeah, that one.
This one right here.
Have ethanol on it, or have an ethyl group.
And okay, yeah, that's it.
Nice and simple to start.
Yep. Easy. Excellent. And that's the only difference. Okay. Let's get another.
Sorry, and that one's an equatorial position?
It's, since this is the anomeric position.
Okay, you can just do a dot, a dash,
Yeah.
or whatever.
So this is, yeah, good point. Okay, I can't erase for some reason. Boo. All right. There we go. Yeah, this is anomeric. Yes. Okay. Nice. Here we go. Oops. Okay. Good. Okay. Now what we have? What is this? Malonic ester, right? And sodium methoxide, which does what?
Take off an alpha proton.
Okay. 1-iodobutane, which is this. So, okay, we can do SN2, right? And then H3O plus heat. So I can't remember what these do, so you guys will have to help. So this is malonic ester, which is a quickly way of making substituted what?
So remember that this has a carboxylic acid product, and that's what the H3O plus heat does.
Yeah.
At the end. So I guess maybe alpha keto. carboxylic acid.
Yeah, yeah. So it's an alpha substituted acid, I think. Yeah, the point is that there's an extra carbon here that, well, I forget about it, and it's easy to forget. And I hardly even learned these when I was taking the class, just because there was so much going on in that chapter that, and these are at the end, and I was like, all right, whatever. So,
Are we just going to get like a pentanoic acid out of this?
yes, I think so. Actually, so we
butane,
have
butanoic.
we have 4 carbons here, and so there's 6 carbons total, right? We have, let's pick a color to count carbons. Maybe I'll go with like green. Okay, here's a nice color, right? So we have 1, 2, 3, 4, 5, and 6 carbons that stay in the end. Yes, so yeah, hexanoic is the one. All right. Let's keep going. Here we go. And this up. Okay. Very good. Just for a bit more. Okay. Well, this one's in Fisher projection, which is already nasty. So what are we doing? We have formaldehyde, acid, and borohydride. So what does that look like? Any thoughts? What if instead of writing it like this, I wrote like that? So now which reaction we're doing?
Reductive amination.
Exactly, right? So here we're
I
just
really
doing
get you with that one with the Fisher
Yeah.
projection.
Yeah, exactly. So yeah, here's reductive amination. So NH, CH3, and a pH here left over. Okay. And then hydrogen peroxide and heat. If I remember correctly, some kind of base goes in this step as well. Although I can't remember exactly what goes into it. Perhaps one of you might.
I don't remember if there's a base involved, but I mean, I'm definitely not the final authority on that, but I don't remember there being one, but that should be, let me see, like adding that alcohol, like one of those OH groups onto the end. And then I don't know if it exists in like a ionic form or not, or if it'll protonate. Oh, wait, what's heat? Let's see.
It's a bit more complicated than that.
Oh, wait a second. Wait a second.
Oh, yeah, no, there's no base. You were right on that.
Is this the one that does the E2? Like does the
Yes.
elimination and then, okay. Yeah. Okay.
Exactly.
Sorry, I'm
yes.
in lab, so I just jumped in late. Is this just the cope?
Yes, this is cope. And so because this whole thing is cope, that means that this is our leaving group.
Yeah.
Right? And there's only one hydrogen that we could pull off of, which is this one. So we're going to pull here, take here, and kick this off. Okay. And so there might be, I can't remember if there's some kind of rule about whether you tend to get cis or trans with cope. Maybe you guys remembered. I think trans tends to be the preferred.
I think you're supposed to get mostly cis. You're supposed to get mostly Zaitsev, I know.
Okay. And Zaitsev is what some of us might call cis. Yeah. So it's the same thing. Okay. So in that case, we would get a pH here, a hydrogen on this side, and a methyl on this side. Okay. Or it might make more sense to put them to swap these two. So here's a methyl, here's a hydrogen. There we go. Yeah. The Fisher projection in this problem probably doesn't help, but well, it's there. So we have to deal with it. Okay. This is a fun one. It's one of everybody's favorites. I don't know if it's your favorite. I kind of like these, I'm not gonna lie, but okay. Methyl vinyl ketone and potassium hydroxide on this thing. So remember, this is methyl vinyl ketone. Is it? No, this is totally not methyl vinyl ketone. I just drew some garbage up. That's methyl vinyl ketone, I think. It is, yeah. So that's it, and then potassium hydroxide. So what kind of reaction is this to start?
Is this just the annulation, Robinson?
Whose annulation?
Robinson.
Yeah. So Robinson annulation. If you just remember like what the final structure is, you could probably just write it instantly. I absolutely can't. So I just remember that this is a Robinson annulation is from a Michael edition, and so let me get a nicer color. Blue. Good color right there. So I know that you would go here, pop here, right? You would do this whole thing, and and then you'd eventually come back down, right? And so the point is that we would come here. Oh, ew. That's an ugly structure. So we would come here, there's an O, right? And we've added on here. So now we might want to count carbons and say there's 1, 2, 3, and 4 carbons that we added. So 1, 2, 3, and 4. 1, 2, 3, 4. Here's that O, right? And then eventually we just want to form, let me use a different color here. We want to form this bond, right? So we repeat this. So we repeat that, and then we get this structure with an OH. Is that right? Yeah, I think so. Yeah, because this is a beta keto alcohol. So that should be good. And let's say that we want to go one step further and heat it. Just get rid of that alcohol, right? And so we'll get rid of that and form a double bond there instead, because this will just be an elimination product. Oops, there's a double bond here, right? Nice. Ah, okay. So what I've written differs from the answer key that I have.
I think
There's
the
a very
orientation's a little different, right?
Hmm?
The orientation might be different
What orientation?
of the rings.
Oh, like where I like attach the two rings together, where the bridge is?
Yeah, I think so.
Yes, it is. And it goes all the way back to over here, because I picked this hydrogen as the most acidic one, but it's definitely not the most acidic. So this is not the most acidic. Okay. This is the most acidic. Let me use a different color. So this one here is way more acidic. Okay, and so this is not right, this is not right, this is not it either. Okay, so instead, what we're gonna do is we're gonna take this one and attack it onto here. Okay, and this is the structure that we started with, and it's gonna go here. And there's gonna be 1, 2, 3, and 4 carbons. Okay, and then we want to form this bond from here, right? So here's that OH. This, I think, is actually one closer. No, it's a beta keto acid. So it should be there. And yeah, you could do the extra step if you want. If you heat it, then you'll get the double bond. There we go. So, well, I guess be sure to look for the most acidic hydrogen because, well, I didn't when I started doing this problem. So look for that.
And that's based on the proximity to the two oxygens.
Yeah,
Okay.
that would be why. It's because it's between two carbonyls, which makes it like doubly acidic.
10%.
All right. Yeah. Okay. Let's paste. And oh, it's right here. Excellent. Great. Okay. Well, there's no slowing down, so let's keep going, right? We have this thing, which is phthalate, I think, right? And then we're giving it base, and then this freaky little guy, and then hydrazine. So what reaction is this?
This is a Gabriel synthesis.
Exactly. Okay, and without worrying about steps 1 through 3 at all, because we know what the Gabriel synthesis does, what do we get at the end?
You should just get a primary amine and then your like Gabriel byproduct with
Yeah.
the rings in it.
Plus junk. Yeah, this is the part that we care about. So that's it. Yeah, there's I guess if you wanted, you could, you could say like, oh, this is gonna pluck the hydrogen off, right? And then there's gonna be a minus charge, and then it's gonna be a good SN1 nucleophile. It's gonna do that, right? And then there's some nonsense happens with the NH2, with the hydrazine. But at the end of the day, if we're just worried about what comes at the end, then this is the one. And maybe you could memorize the other Gabriel stuff that comes out at the end, but probably not worth it. Let's keep going. We have more. I paste it. Oh, okay. So, okay. Let's see. Okay, so we have an ester here, and we have sodium methoxide. What is going on at all here? Like what reaction altogether?
Hydrolysis of the ester.
Of this ester?
Yeah.
Well, let's say there's no water at all here.
Oh, okay. Then no.
Yeah. No, so yeah, hydrolysis won't work. Right, and you can't do any like transesterification because we'll have, an ethoxide, right? And we just replace an ethoxide with an ethoxide. Okay, no point, right? Nothing happened.
Yeah.
So we got to do some other stuff. what if instead of this, I wrote this? I just wrote the same thing twice. But, oh, there's a reason for it.
Would this do a condensation?
Yeah. And actually, since this is an ester, this is a Claisen condensation.
All right.
Not that the name really means anything, but yeah, we would make a minus charge here, throw this on, and kick off that O-ethyl group. And at the end of the day, we are left with, here's an O-ethyl, here is a beta keto ketone, which is what we get out of the Claisen condensation. Okay. Okay. More sugars again. I could see that most of these problems are from the latter end of the course, but you know, it's okay. The ones that I found weren't, so that's, we'll get a balance. Okay, here we have this bromine water. I don't really remember what that does, so this one's up to you.
This is a rough degradation. The bromine water does the, like, makes that top aldehyde into a carboxylic acid, and then the hydrogen peroxide takes off the acid at the end.
Okay, so it's just a rough degradation. So CHO, and then I even drew one too many carbons, I guess. So CHO, and then we just pull off the top one. And OH.
So then
lithium.
the extra methyl lithium will methylate all of the alcohols because there's excess.
So that would be if it was methyl iodide, I guess, right?
Oh, yeah.
But
So,
we do have that aldehyde.
right. So you just methylate the aldehyde then, right?
Yeah.
Okay.
So we'd actually form an alcohol there. And so here we would get OH, CH3, something like this. Okay. Interesting. The answer key that I have says you get a ketone out at the end. That makes sense, I guess, though. Because, and oh, this would be why, I think, because we don't get an aldehyde here. I think we get a carboxylic acid. CO2H. And so when you add excess organolithium to CO2H, then you get a ketone back at the end. Because
So does in like a regular like rough degradation, the evolution of the carbon dioxide gas is like to take off that top carbon? Is there something that precipitates that we kind of like didn't talk about? Because the like when we talked about the rough degradation, obviously that third step with the methyl lithium wasn't like part of that. But like the product of the degradation is just to like evolve that CO2 and take off the top carbon.
Yeah. And yeah, and I think it leaves a carboxylic acid behind. So it definitely is to get rid of that top carbon. I'm gonna check because this is worth checking. If it leaves an acid or not behind. Reactions of sugars. Okay. Are they gonna tell me a rough degradation? Oh no, at the end it does leave an aldehyde. Okay, then my answer key is wrong. We were right. This is good.
Okay, cool. Okay.
Yeah. Yeah, it does leave an alcohol behind. Yeah. Good. Yeah, if we had an acid here up at the top, like let's say we did bromine water again, just to turn it into an acid, then
Right.
Then we would get a ketone at the end.
Mm-hmm.
But we didn't. Okay, good. Good. We're really achieving speed, so we will do a lot of problems. Still plenty more. Where is it? It's up here. Okay. Okay.
This looks like reductive amination again.
Yes.
But more complicated.
Yeah. Okay. Yeah, it does. I was thinking for a moment if we were gonna do something else kind of complicated, or if we were gonna like if we were gonna do like a Michael addition, but we're not because this is electron donating, not withdrawing. Or if we were gonna make an enamine here, that's too complicated. Yeah, it's definitely a reductive animation because we have this guy here. So, well, I guess we don't have to think about this one that hard, right?
Yeah. I'm just gonna
That
in there.
that looks like it.
Cool.
Yeah, I think that's the extent of what we need to do for this problem. Let's see if that's right. Yeah, that's right. Okay, cool. Double checking because it was way too easy. Okay.
Don't jinx it. Maybe the final exam will be this easy too.
Well, that wouldn't be so bad.
Yeah.
Yeah. Although, yeah, maybe the problems that I pulled will we'll get all the hard problems out of the way, and then the final exam will be easy too. So who knows? Okay, we have methyl iodide, which does what?
Just gonna methylate.
Like,
Methylate here. Yeah, right. Methylate, silver oxide and water, and then heat.
that's the Hoffman elimination.
Yeah, exactly.
Yeah, you're gonna
So this is
lose your
Hoffman.
nitrogen containing part.
So yeah, we'll lose the thing with the nitrogen, and let's see, we have to pull a hydrogen off somewhere, right? And it needs to be somewhere that's 2 carbons away from the nitrogen, right? We can't pull this one off. This is too close, right? no hydrogens on the phenyl, right? And so over here is also too close. Okay. So we have to pull this hydrogen off. So let's pluck that off. These electrons go up here. This gets kicked off, I think. Seems right. And then we wind up with ethene. Wow, very, very, very complicated, right? And we wind up with this thing, which is what had our, which is what was holding this whole thing to begin with. Does that look right?
So we need to, I'm just confirming this. For a Hoffman elimination, you have to use a beta hydrogen. You can't use an alpha hydrogen. Okay.
Yes.
Okay,
Yeah.
cool. I will remember that because I didn't before.
Yeah. Good. So this is it. I haven't done a Hoffman elimination in ages, so I'm glad it looks right. I also checked the answer key. It's right. So that's a plus. Oh, this is a big one. Okay. Let's see. What the hell is pyrrolidine? I don't know.
I know
what
it
this
has
is.
nitrogen in it. That's about it.
Yeah,
Yeah, it's just gonna make an imine.
Yeah.
it's gonna be this. So step one, make the amine. Okay, good. Right. Step two, methyl vinyl ketone. Oh boy, what's that? What reaction are we doing now?
It's gonna add to what would be our alpha carbon.
Yeah. And so which of these is it? Is it one or is it two?
I'm not sure. One?
Are you just guessing one?
Yes, I am.
Okay. You had a 50-50 chance, and I don't think it's one. So yeah, so I think it's two.
So you specifically
two-
want to use like the less substituted spot.
Yeah. So two will be a better nucleophile because it's less sterically hindered, and it can also hold a minus charge better. Which makes me say two, but well, it could not be two. It seems like it would be though. So, and okay, even if it's not, we'll be off by a carbon, right? Not a big deal. So we do our Michael addition because that's what we're doing. Okay, let's draw this, right? And methyl vinyl ketone is this thing right here. Yeah. And so carbon 2 came up and attacked here, right? And then threw this over. And I don't know, somewhere you lose that electron pair. I don't know where, but at the end of the day, we have 1, 2, 3, and 4 carbons left over with a ketone on 3. Okay. So LDA will do.
I know it'll deprotonate. Let me see. It will.
Yeah. Okay. Yeah. So yeah, LDA deprotonates, right? So we'll come here, steal this. So it deprotonates there, and then what happens? This one's a bit tougher.
Does anything happen with the heat, like before we move on to adding the cuprate? Like, does that change anything? Or is that just like part of the LDA, like being a good base?
No, I don't think you would normally need heat for LDA to be a good base.
Right.
I think it means that some additional stuff is happening.
Okay.
Oh, is it? Maybe. So I'm thinking this can go one of two ways. And maybe one of you guys can say which of these ways is bad or which is good, because I'm not sure. So one possibility is that we get the whatever this thing is called, the enolate, to attack here, kick these electrons up, steal hydrogen. Something like that.
Yeah.
So that's one possibility. Okay, this is the red path. And then from there, let's see, step 4 is to give it a cuprate, but the cuprate won't attack here. So the cuprate doesn't really do anything, right? At best, it'll just steal a hydrogen off here because cuprates are pretty basic.
Right.
So this is a kind of okay. This way kind of sucks because of that, right? So that's why I think it wouldn't be that. The other one, the other option, which is quite complicated, and well, I wouldn't really expect people to figure out, is that these cuprates, or sometimes they're called Gilman reagents, these are, oh no, that wouldn't work either. So I was going to say there might be some Michael addition stuff, because I remember that these are really good at Michael reactions, but they're only good at Michael. These are Michael donors. They do the attacking, right? But then we have an enolate here, which will also do the attacking. So like, not very useful. So maybe not. I'm going to see what the solutions say we should do.
Yeah, I'm like looking back at old notes and problems and stuff, and I don't ever see LDA and heat in one step. All I ever used it for was like simply to pull off a proton and make the enolate.
So this is why. So it's LDA and heat because what it will do is pull this off and form a double bond,
Oh,
which we could do.
okay.
And then this last one is not really something that I think we've talked about ever. You could do these sort of, oh, nope, just kidding. This one we can figure out. Okay, this is a cool
So
problem.
since you have that double bond now, wouldn't that become a Michael acceptor?
Yes, exactly.
Okay.
Yes, excellent.
Yay.
So now we take this, which is a Michael donor. And here we have a Michael acceptor. Yeah, exactly. Right. So we do a conjugate addition here. Now we go, whoop. Oh, oops. Come around here, whoop. And whoop, whoop, whoop. Right. And then at the end of the day, I don't know what happens to the double bond again. You do some tautomerization nonsense or something. And
Yeah.
yeah. And at the end of the day, we get we still have our ketone here. We've added this. We have our methyl. And that's it.
Cool.
Okay. So I guess walking back through that. So one, we made an enamine. I guess an imine, but they're sort of the same. Step two, we did Michael addition. 3, we did a condensation. 4, we did Michael addition again. Right, and this is Robinson annulation. Okay, it's weird because we used an enamine instead of a normal ketone or normal enolate or whatever, but at the end of the day, we got the same thing out. So it's pretty much a Robinson annulation. Although,
Wow.
yeah, it's it. It's simple.
Easy to see.
Yeah. Yeah. So. Okay. Here we go. This is okay. So now we have a synthesis problem now. So this one's a bit weird. And looking at it, I'm not sure how to do it, but maybe you guys will have an idea. Yay.
Interesting.
Synthesis. Yay. OH on a nitrogen. That's really weird.
Yeah, that is weird looking.
Yeah. So, yeah, unusual. Well,
we can just make the imine using, you know, whatever, however many carbons that is. It's what, 3 carbon. Amine, am I muted down? Amine. So since you already have the aldehyde, you just have to add the primary amine with some acid. And that would make an imine. Oh, but wait, wouldn't that? I guess that kind of puts things in the wrong spot. Perhaps.
Yeah.
Huh.
So, okay, maybe we should start on this end. And do you think that we could, not that I know, do you think that we could do, just starting with this, we could just add something that's like NH2OH and then acid?
Maybe.
Yeah, seems like it could be reasonable.
Yeah.
Okay, so that's something to work with, right? And so maybe we'll scrap this direction. And I guess now, well, this isn't actually so bad, right? Because we're just getting this chain. We're just elongating the chain on this aldehyde. So we can actually do this in 2 steps.
So could you just add like a organolithium or something and attach some extra carbons?
Yup. 1, 2, do an aqueous workup because we like that. Whoops, that's not right. There should be an alcohol here now. Okay, and then
PCC.
PCC is a good choice, or Swern, or DMP, or bleach. You know the deal. Yeah.
I basically never use anything other than PCC. It's fast to write and it gets you there. Just
Yeah.
easy is best.
Yeah, that's completely fine. Yeah, the rule is always there's no points for being creative. So yes. So write down whatever is easy for you. I usually just blast Swern at things because you don't even have to write anything.
True.
It's just a word. It's just such a nice thing to write. Yeah. Okay. I think that's a pretty good synthesis route. Wait, what? Okay. Okay, I just looked at the solution and there's some complicated thing here. So why don't we, okay, maybe we'll try to work through the solution. I think that what we wrote was perfectly fine. I don't know why it wouldn't be. But let's maybe take another look at this problem, I guess. Okay. Yeah. I would have gotten what we wrote. So okay. So this solution says, okay, this is really weird. So step 1, although I think I've seen something like this before. So step 1 is add, it already gets weird. Add this thing. Yeah, I know. This is really weird. So this is gonna form a thioacetal. I think that's what it's called. So it'll form that. And then it says, give this N-butyl lithium.
Okay.
Which I think is capable of deprotonating here.
Oh, okay.
Of course. Then give it, you could just give it this bromide. Right. And then you give it a mercury salt and acid. I guess that just gets rid of this thing.
Okay, interesting. So this just must be like some sort of like protecting group that we just never like really went over, because it works exactly the same as like a what is it? Maybe glycerol. I don't know. The one that is essentially the same as the SH, but has OH that protects an aldehyde.
Yeah.
Okay. Interesting.
Yeah. So I've the professor that I had for Orgo 2 at the very end mentioned this as like a conceptually different like synthesis pathway, because in what we wrote, we were using the carbonyl as the electrophile and the
Mhm.
Grignard as the nucleophile.
Mhm.
But here, we're using the carbonyl compound as the nucleophile, and this is the electrophile. And so we've kind of swapped the roles. There's
Mm.
some fancy name for this, like as a conceptual
Yeah.
strategy. Um, although I have no idea. I can't remember what it's called.
Okay, so but
Um,
the last step, like we essentially just got to that last step a totally much more simple way, and adding the NH2OH with acid is exactly right. Like that's fine to get that weird
Yes.
like double bond nitrogen OH thing. Okay.
Yeah. What we did was totally fair and correct, and
Okay.
fewer steps than this. So I don't know why this was in,
Right.
this is a complicated thing. So
Right.
yeah.
And in practicality, like trying to avoid using mercury when possible is probably better, I guess.
Yeah, I would think so. I really would. Yeah.
Okay.
I know it, so it's a good synthesis strategy when you have to avoid using Grignards or lithium things.
Right.
Like I'm pretty sure that is practically speaking the point. But doing a Grignard or whatever is like not an especially hard reaction, so I have no reason to.
All right, benzene.
Yay.
Fun.
Yes.
Okay. Well, let me look back at benzene stuff. So I know adding that Cl would be super easy, but let me pull up that super handy dandy thing. I think that the Cl is a meta directing group, so that should be fine to do it first.
So it's the other way around.
Oh, it's orthopair. Okay, I was like looking at this chart thing again, and it being in green threw me for a second. But yeah, so
yes.
yeah, and that's the special case where it is deactivating, but at the same time orthopair directing. Okay, cool. Good to remember that.
Yeah. It's weird.
No.
So adding the chlorine on first won't do it.
Right.
Yeah. So I guess we'd rather add the carbon chain on first, right?
Mm-hmm.
If we want the carbon chain to be meta directing though, what reaction should we do?
So let's see. Aldehydes, ketones, esters, acids. Okay, so we could do a Gatorman cook. We could just simply isolate it like a Friedel Crafts.
I like that one.
Right? Okay.
Yeah, that's a good option because we can get all of our extra carbons on at once.
Yeah, okay.
And what does this need? Aluminum trichloride, and I think that's it.
Yeah, that's it.
Yeah, so that will get our extra carbons on, and final draw it out like that, right? And now this is meta directing, which is good. So now what?
So we just need to, I don't know, should we add the chlorine or do you have to change it to the N3 group? Because I think you could just, right, like you can just add the N3 and it will, I think of something different.
Yeah. So if we add the N3, right, we have this whole group,
Mhm.
but this whole thing is also ortho-para directing.
I gotcha. Okay, so we should just do the chlorine, which
Yes.
is, I think Cl2 and AlCl3.
This will probably do the job. I don't remember very well either, but
Okay.
I think this should work. Okay, and so this will guarantee
Yeah.
meta addition. And now we just need to swap this out with an N3. Any ideas on how? There's no really pretty way to do it, I think.
Oh, yeah, because we need a leading group. Hmm. No, like the only, I mean, you would obviously need to have.
Well, how are we going to attach the N3 at the end of the day? Like what reaction?
I don't know. Remember working something too much. Or is it just, I mean, it's just going to be like a substitution, right? Like,
Mhm.
okay. All right. I was thinking it was going to be more complicated than that.
Nope.
Okay.
So here we're just sodium azide, which goes by SN2, right? And so we want some leaving group.
Right.
Oh, there's several leaving groups that you could pick here. Yeah. I don't know. This one's up to you.
Okay. So just to reduce that ketone, we could just use like LAH, right? Yeah, that guy.
Mhm.
And H3O plus.
Okay. OH is a pretty bad leaving group though, so
Mm-hmm.
how do we make it a good one?
Let's see. And you could just add like hydrochloric acid or something and put your like some strong HCl or HBr and go from the alcohol to the alkyl halide.
Okay. That's an option.
What would
If you
do?
want to go with an alkyl halide, I might also suggest that that's one way to do it, although that's like not great because it goes in equilibrium and you might get some elimination product.
Yeah.
So you could also do like PBr3.
Oh yeah.
Is a good option.
Oh yeah. Duh.
Another, yeah, no. It's really easy to forget these. Another good way to make a leaving group out of an alcohol is with tosyl chloride.
Okay. Okay. Mm-hmm.
and you need some kind of base along with it.
Okay.
That's another good way. Of course, PCl3 would also work here and so on.
Okay.
Yeah. So that's a good way to do it.
Okay. So we did, let's see. Juice.
All right. So we're starting with the nitrile, and I guess we're getting rid of it. Very fun.
Oh yes.
This
Times ahead.
This one actually looks pretty hard. So let's try it.
Still copying it down. Okay. Yeah, interesting. So we have to get rid of the entire nitrile, not just the nitrogen itself.
Yeah.
Okay. Let's see.
I'll remove that. Okay.
Hmm. I remember a way to like, there's like a way to reliably make a higher substituted amine, but it would like the only way that I could think to start this would be to reduce the nitrile, and that would keep the carbon. So that's not what we
Yeah.
want.
Yeah. Weird.
Like, how could you kick off that carbon? It's such a strange thing to do. Well, I guess it is. It could be a good leaving group if.
I'm taking a look at the solution, and I'm not sure I really.
You don't vibe with it.
No, I don't really think so.
Interesting.
Yeah. No, I don't think this is great. So I can show you what the solution says.
Yeah.
I don't really like this one that much. So so first thing is to hydrolyze. That's like one of the only two things we could do with this.
Which would give you an acid, right?
Yeah, exactly. And then it says to make this into an amine. So we get an amine out. Which is all fine, right? This, I mean, it's weird. It doesn't make sense why we would do this, but whatever. The reason that this gets weird is because it then says to give it bromine and hydroxide, which does a Hofmann elimination.
Okay.
But I mean, well, this is an amide, so I haven't seen a Hofmann elimination with an amide before. That's already weird.
Maybe they meant to like reduce that carbonyl off first. But that still wouldn't make sense because then the nitrogen's not in the right spot. like it's one bond over too far from the, right?
Yeah. There might be a special case of like the Hoffman elimination
With
with
an amide?
amides.
Yeah.
And so this should take a CO2 off.
Oh,
Yeah, that it will definitely do. I'm gonna look and see if the book mentions anything about Hoffman elimination. Wait, this is already, what? How's this a Hoffman elimination? Okay. This is not like that.
like at least with the Hoffman, they usually like have to specify that there's excess of something to like, and it has to be a methyl, like a methylating, like, methyl iodide or something, and methylate it. So it's like a really good leaving group, right?
Yeah. This is why I think this is weird.
Yeah, I don't trust
I
it.
don't know what this does.
Huh.
Like, I'm just not sure. It somehow has to get rid of this CO, and it's probably in a CO2, but I'm really not sure how. Yeah, Hoffman normally uses excess methyl iodide, and then it uses silver oxide. So, well, I'll quickly check the section in the book on amines and see
All
if
right, I'm
they
gonna
have
see if I
anything.
can find anything in my notes about bromine precipitating evolution of CO2. Right, because I don't see how that would work, but I'm gonna see if I have it in my notes somewhere.
Yeah. Chlorides, esters, no. Yeah, it's so nice. Nope. The amide section in the book doesn't have anything.
Yeah, I'm not finding anything either. Although, oh, Hoffman rearrangement, amide plus BR2, I have NaOH written, it's obviously the same thing, makes an isocyanate. And then, at least I've written down water, like add water, and then CO2 is evolved after that. And then you just have the primary anion.
Okay.
Yeah, less the one carbon.
Wait, where is this? Where's this from?
I don't know. I don't have a I didn't write it down from the book, but I have it written down. I may have like seen it online at some point and written it down when we talked about isocyanates.
Okay.
And
Did Dr. Song talk about isocyanates at some point besides protein chapter?
yeah, he talked about it. Oh God, maybe chapter 21, like the carboxylic acid derivative chapter,
Mhm.
I want to say,
Oh, okay.
which doesn't really make sense. But that week was like a really weird week for me because I ended up having to stay at work really late the night of the lecture, and I like wasn't able to watch it on the one day that I like blocked the 3.5 hours to watch it. So I
Yeah.
was behind like that whole week and was kind of like playing catch up. So yeah, I like vaguely remember that, but I was kind of like not really on top of my shit that week.
Oh. Well, I've never seen this reaction either. So, well, I mean, I guess you've seen it at least.
I
I've
have
never-
seen it. I can't say that I particularly remember it, but I'm gonna, you know what? I'm gonna Google it. Let's see.
Right.
Okay. The Hoffman and Curtius rearrangements. Yes. So Hoffman and Curtius rearrangements are two examples of a whole family of rearrangement reactions that share a common mechanistic step. In the Hoffman rearrangement, an amide is treated with bromine and a base. Upon heating, an intermediate isocyanate is formed, which is not isolated. In the presence of water, the isocyanate loses carbon dioxide to give an amine. The key bond that forms in the Hoffman is the C2N bond. Note how the carbonyl group is lost, forming carbon dioxide. Yeah. And then I guess the Curtius rearrangement is the same thing, but with an acyl azide. So yeah, I don't know. We definitely never went over like an actual mechanism for this, but
Yeah.
perhaps,
This sounds a bit involved.
yeah, perhaps this is something that we, could use like in a synthesis. I don't know. Again, I need to go back and kind of like look at that one chapter that week, because like I said, I was off my schedule.
Yeah.
And didn't like super solidify much of that information from that week. So, but yeah, I guess that is what happens.
Yeah. I mean, okay. This seems useful, I guess.
Yeah.
It lets you get rid of a carbon.
Right. That's always a good thing to have in your pocket.
Yeah, I know.
Not an easy thing to do. All right. Well.
And then from there, we need to add these two groups. How do you want to do that?
Oh, let's see. Well, we could just do, I mean, can't you just use like a alkyl halide? I don't know. Well, I guess all the reactions I have with alkyl halides have like a different group other than just the primary amine. So let me see here.
Yeah, you could probably use an alkyl halide and be fine.
Right. And just
Yeah.
like, I don't know if you need to be specific about like using however many equivalents or whatever, since they're two different substituents.
You're right. So if we were to say add methyl iodide.
Right, like you'd methyl everything, right? I mean, like both groups would be methyls, right?
Yeah. So, okay, maybe we have to be a bit more careful.
Yeah.
Right. So what else is an option? I don't know. I have a lot of stuff written down for diazonium salts, but that's not relevant. I wish it was, because I love that reaction. So easy. I know, yeah.
But not the case here. That's not what we want. I remember doing a problem like this in this chapter and having the same thoughts, like how do you add two different carbon chains? So let's see. I don't know, am I missing something that's like super simple?
It's not the most simple thing in the world. What if I were to write it this way. We'll give you, let's say we just want to add the methyl.
Your reductive amination.
Yeah.
Wow, I need to be a little bit more agile with how I view that, because I clearly, like, when you draw it out that way, I was like, oh yeah.
Yeah. Yeah, it's really weird whenever the reactant is put in this position.
Right. Yeah. Okay.
And yeah.
All right. So.
So yeah, exactly. We could do reductive amination.
Right.
Right, and then I think you need like acid. And so that attaches one. Right, and just do it again.
Yeah.
So now it's this and this stuff again. And that's it.
Cool.
Yeah. Yeah, so this part is weird.
Yeah.
I've never even seen it before, so.
Yeah, I definitely don't think that we like super whenever that, but since it's a thing, I'm gonna keep it in my back pocket for if I ever need to get rid of a carbon. And there's a
Yeah.
Yeah.
Useful.
Okay. All right.
Okay.
Oof.
It's the last problem on our worksheet. And then I get to have fun. Give you some that I found. Okay. What do you
All right,
think?
so this one's a little bit chiller, at least. So NO2 and so NO2 is meta-directing, but an amine is orthopara. So we'll just put an amine on the ring first.
Okay. How?
Yes, how?
Oh, we could just use nitric acid, right? HNO3, H2SO4.
Oh yeah. So we can, that adds the NO2, right? And then we can just reduce that. And then we can add like methyl iodide or whatever to put the two methyl groups on. And then just do the.
So methyl iodide isn't great because it'll add 3 methyls, but
Oh, right.
okay, whatever. 2 times reductive amination. Okay. Good.
Yeah, and then we can just do the same again. Or HNO3 sulfuric acid.
Okay, that works.
Yeah, I like that caliber of problem way better than the last one. I'll deal with those.
Okay, yeah, this is a good option. I briefly peeked at the solution. There's a different way of doing it,
Okay.
which I haven't thought about much. Although, yeah, this is a pretty nice way, which is very easy to forget about, but it's there. So we could take this chlorinate. Okay. What do you think we're gonna do for chlorinating?
Jeez. Your salt, right? Can we do a salt?
Huh?
Oh no. We need a NO2 group for that too.
Yeah. I mean, at the end of the day, we're, this chlorine isn't in the final molecule, right?
Right.
So.
But yeah, so clearly you're gonna have to either kick that off as a leading group, or I mean, I guess that's really the only thing you can do with it, right?
Yeah.
Which I don't know why you'd add that extra step. I guess in my head, I'm like, just add the nitrogen, but
So here we could add the NO2 because it's orthopara directing, right? And then from there, well, we have the right positioning. We have a strongly withdrawing group. So.
Oh, nucleophilic aromatic substitution.
And this will go pretty easily.
Yeah. Oh yeah.
Yep.
Cool.
Yeah, and so here we're doing this makes it easy to do NAS. Yeah. This is ugly because it involved this step.
Yeah. I hear you. Okay.
Yeah. That's one way to do it. Okay. Cool. Shall we look at some problems that I selected?
Yeah. I got a couple more minutes. I can stay maybe
Okay.
10 more minutes.
Sure. Why don't I just start writing a bunch of them, and
Okay.
you think about them.
Okay.
So not nitrogen. Which is the most basic electron pair on each of these molecules. Or here or here. And this molecule's not done yet. That is it. Okay, that's one of them. So this is one. This is two. This is a different, separate problem. Next. Okay, I didn't write the full thing down for that one, so we'll skip it. number 4. Oh boy. Oh no. This is when I started picking the really big ones. Sulfur, and there's a methyl group here. Of course, you just put it in acid and have to figure out what happens. It's like the worst kind of problem.
Oh my god.
I think I can fit like one more. Okay. Oh geez, this one's big. Maybe I'll write a smaller one here. Pick which of these molecules is more acidic. Oh, it's not a sulfur. It should be a nitrogen. Okay. So there's a couple.
All right, let's see. So the most basic electron pair. No, I didn't write that down.
Actually, can you layer? Okay, cool. Now I can draw on this layer and hide the answers if I want.
So in asking what the most basic electron pair is, like it just in terms of like a Lewis base, right, that wants to accept a hydrogen.
Yeah.
Okay. So
We have electrons here,
mhm.
here. Here. Pair here and a pair here.
Right.
This is for each molecule. They're not asking you to compare.
Oh, okay. Okay, that makes more sense, I guess.
Okay.
Okay. Per molecule. All right, well, let's see. The first one.
Okay, yeah.
I guess the first one would be the nitrogen that doesn't already have a hydrogen on it.
Mhm. Yes.
Okay. This is sort of like a weird, I've never actually thought this way about any molecules, like which one would have the most basic electron pair. So, and then the second one, the non-carbonyl oxygen, perhaps.
Yes.
Okay.
I think so.
Okay, and this one, I want to say the bridging nitrogen, but I don't
Okay.
really know why. Or maybe not, because that would be, it's sort of like tougher to get to hysterically.
So why did you say over on this first one that this bottom nitrogen was more basic?
Sorry. Because of that conjugated bond, the double bond there. So I guess, yeah, that would make sense for on the other one to be that top nitrogen because of the stabilization.
Okay. So you are correct, but for the wrong
The
reason.
reasoning is not sound.
Yeah. It's because of what I wrote here, which is that these electrons are orthogonal. So what happens is this here can resonate. In fact, you need it to resonate for this whole thing to be aromatic. But this lone pair on the bottom nitrogen can't resonate
Right.
because that nitrogen already has 2 double bonds. So
Got it.
or it already has a double bond.
Mm-hmm.
Yeah, so it's never tied up in resonance, so it's good. Here, one of these electron pairs on the oxygen is tied up in resonance, but
It's
well,
not.
the other one isn't. So
Okay.
yeah.
So
So I believe lone pair on the oxygen atom. Nope, just kidding. All right, this one's wrong.
No.
It's not correct. So it's not because, so this one's not it. It's actually on this top one. And the reason is, boy, if we protonated,
Mm-hmm.
then we would get an OH plus here. And this. And we can move these electrons up, kick these
Right,
over,
right.
and push
Yes.
this on. Which, if we do this, yeah, at the end of the day, this is aromatic.
Yeah.
That would be why. Okay. And then yeah, this one's good.
Right, sweet.
Yeah, for a fun fact, this here is if we attached it to an amino acid. This is called histidine. It's one of like the most commonly reactive amino acids.
Makes sense.
And then somehow you attach this to an amino acid, I think, and you get tryptophan. I think so. Although tryptophan, oh no, just kidding. It's closely related to tryptophan, but it's not. It's not right. Okay. Either way. Okay, we won't worry about this that much anyway. Okay. It's a bit crowded here, but what's going on in this one?
This one feels like a really old reaction that I need to pull out of the depths of my experience here. Well, so what I think will happen is that double bond will do like a nucleophilic attack. Oh no, that's not a carbonyl. What am I talking about? Let's see.
Yeah. In fact, this is a reaction that you could have gotten back in like late October or something, and
Oh, that was
way back.
like
Yeah.
years ago.
Yep. I wonder where I got this one. I don't know why it was on this list. Okay. Well, I thought it was a nice problem anyway. Whoa. All right. Wait. Okay, this problem is way more complicated than I thought. Never mind.
God.
Okay.
All right, I feel a little
Um,
less bad.
Yeah, this is actually a challenging problem. Okay. Um, so my thought, and it turns out that I guess I'm very wrong, is that you can, whenever you have a double bond and you have, if you have a double bond and acid, it'll just hydrate the double bond. It'll do this.
Oh yeah. Oh my God, that really feels like a forever ago thing.
It's really old. But so okay, so this is so you could do that. And so if you have an alcohol just in general, then you could kind of just overall you have any alcohol and acid, you can make an ether out of it. So that's what I thought this was about. It turns out that I'm very wrong though. So this is quite a lot harder. And so what you can do instead is if you put this in acid, you will get this cation.
Okay.
And what do cations do with aromatic compounds?
Let's see. Cations, rearrangement. I'll add, substitute onto a aromatic compound.
Yeah, they will. Alternatively, if I had written the compound like this,
Yeah.
right, then we would get this. And so it would just be a Friedel-Crafts alkylation.
Right.
And Friedel-Crafts alkylation has the downside, although in this case it's not a downside, that when you alkylate, it gets more reactive. And so you'll alkylate again.
Yeah.
So in this one, we alkylate twice. And I'm going to rotate this on its side. So that's what we get.
Interesting. Okay.
Yep.
Probably never would have come up with that.
I would not have either. I thought this was a much simpler review problem. Oh,
Interesting. Right.
I guess not. Okay. Over here, let me get rid of this silly question mark because it's just eating space. Okay. All right, now what do we have?
So that first one is like a Wittig reagent, right?
Yeah.
But that reacts with the carbonyl. So because this is protected and we're not adding any acid or anything first to unprotect it. I don't know, like would it break open that weird dioxide thing, or does it just do the reaction as it would as if it were still carbonyl?
So this is before the Wittig reagent.
No.
So the Wittig reagent will normally have like, some other stuff.
Oh, right.
On it. But this one doesn't. It just has this lone pair. So
Okay, so it'll just like kick off that that chlorine, do the attack, and then now it's like an actual Wittig reagent.
right, and so one we have this, This N-butyllithium is just the second step of making a Wittig reagent.
Okay, I gotcha.
So here we have 1 + 2. So we made our Wittig reagent. So now we add butanol, which looks like this. Okay, and so now what does the Wittig reaction do?
So that the double bond onto that P group will like essentially be, yeah, where that aldehyde is, where the carbonyl is, and then you'll attach all that extra stuff.
Yeah, so here we join these two. So this is step 3. Okay, so here we have this double bond, and now we have the carbon at the end, 1 carbon, this whole thing, and another carbon. And now H3O plus.
Yeah, the acid will just take that back to a ketone, that little
Yes,
group.
it will. There we go.
Super fun.
Yep. Good reaction. All right. This is this one's always good. This. Oh, let's go back here. Okay. Now, well, now
All right, acid. Let's see, what kind of functional groups do we have here? I would guess that something would happen with the sulfur, but I need to go back and see what I'm dealing with here.
Okay. Sure. So, the thing about this sulfur is actually that it has these lone pairs and these electrons here. So this whole ring is actually aromatic. So nothing's going to happen to it.
Oh, I gotcha. Okay.
It's here to stay.
Okay.
So that part's off limits. Okay.
So maybe that double bond that's in between the two nitrogens, because that would be not, wait, one.
Yeah, that's a good place to look.
Yeah, I mean, would it just get rid of that double bond, like pull the nitrogen, like protonate that at that carbon? It just feels like
Somewhat.
so simple.
What if I did something really, really basic and just said, forget about this, forget about all this. What do we have?
An imine.
Yeah, that's it.
Oh God.
It's just an imine.
Okay. Well.
So if we do this, right, then all that we're left with here is an imine. Yeah. Okay. Then, so yeah, all that happens at the end of the day is that we cleave the imine. And it's a huge and very complicated thing,
Yeah.
but there's not a lot going on. And
Fascinating. Okay.
yeah, and every once in a while I like problems like these because I don't know, I guess it just reminds you to not overthink it sometimes.
Yeah, I definitely was. Okay.
So here's those, and there's a methyl. Okay. Oops. That's it. Cool. Okay. So which of these is more acidic? I have no idea. I don't like these problems.
Yeah. Well,
So
let's see. Oxygen is more electronegative than nitrogen. Nitrogen already has H on it.
yeah.
Well, so if you have like a more electronegative, like the oxygen there would kind of make your acid more acidic, right?
I think so. Yeah.
That's what makes sense to me, but yeah.
Yeah, I think so. Why don't I actually check? Because I was never very good at these. So I like to check. And because I know where I got these problems from. So. Yeah, here. 12.1a. Yep. Yeah,
Yay.
that is exactly why.
All right. Well, at least some of my instincts are still intact.
Nice. Yeah. I definitely would have overthought this one. So good. Okay.
All right.
All right. It's one. So
Yeah.
we'll
Thank you so much,
stop there.
Adam, for guiding me through these many chapters of organic chemistry.
Yeah, I know. Yeah. Yeah. Thanks for coming. I'm glad I could help in any
Yeah.
amount. So
Almost done. Right at the end.
yeah, I know. Yeah. And you could you now have the pleasure of, I mean, at this point you know as much organic chemistry as I do. Truly. Because well, now you just have the final and you don't learn anything on the final. So
Yeah. Or you shouldn't be, at least.
yeah, hopefully not.
Yeah.
Awesome. Okay.
Thank you so much.
Yeah. Good
Happy
luck.
graduation and have a great summer. Enjoy it.
Yeah. Yep. Have fun never doing organic chemistry again.
Oh yeah, I very much look forward
After
to this.
after Tuesday or something, right?
Yeah. All right.
Yeah. Okay.
Bye.
Bye bye.